We're going to be switching gears. I know there's a lot of discussion on systems, networks. We'll be talking about circuit design, hardware, how AI as a potential tool can help us design better circuits. Not just design, but all aspects of productization of chips from conception to high volume production. I'll wait for Ian just so that he's...
Just went on a bathroom break.
Okay, that's good. Hey, Ian. Okay, that's no worries. Okay. No, we're just kind of introducing the topic. How all day we've been talking a lot about networks, systems, AI for channel estimation, image processing, and so now we're switching. Like, how do we actually use artificial intelligence to design circuits? And I'm a circuit designer, so I started working at Qualcomm about 30 years ago. We didn't even have very good tools back then, but that's one of the things that when tools like SpectraRF, harmonic balance came on, we were able to design circuits with much better predictability, particularly analog and RF circuits, which were very difficult to design at that time. So now we're kind of at another sort of stage where we have another potential tool that can change the way we design, test, and manufacture these circuits. So I just want to quickly have each of the panelists introduce themselves, and then we can start with some of the questions that we prepared.
Hey, I'm Ian Galton. I'm a professor in electrical and computer engineering at UCSD.
I'm Thomas Anderson. I run the AI machine learning team at Synopsys.
Hi, I'm Naveen Yanduru. I'm the general manager for the RF business unit at Renesas.
Good afternoon. My name's Mark Pierpoint. I'm responsible for strategic innovation and partnerships at Keysight. So long-term strategy and, not surprisingly, talking about AI a lot these days.
Hi, I'm Michael Thompson. I'm a distinguished engineer at Cadence Design Systems, and I work in the development of Virtuoso product lines and platforms.
All right, great, guys. So yeah, as you know, a lot of compute power has realized and allow neural networks to be sort of part of our daily lives. So how will neural networks change and artificial intelligence change the way we work? So some of the thoughts are that there could be optimizers. Very good optimizers are already being integrated into commercial tools like Cadence and Synopsys. There could also be a co-pilot. I know there's a product offered by Synopsys where it's you have a co-pilot for design. So instead of looking at the design manual or software guides, you're able to sort of quickly pull up information. I was always motivated by trying to be lazy. There's a lot of aspects of circuit design that are repetitive, require a lot of data analysis, rerunning things. And once we were able to sort of automate, it makes life easier. So I think this could be another step for sort of really automation. But I'd like to hear from maybe Ian, what's his thoughts on how artificial intelligence or AI will change the way we work.
Okay. So I should first of all mention that I'm not really qualified to be on this panel. My main qualification is that I'm a grumpy old man, and so I'm somewhat of a pessimist by nature. So back in the late 80s, I quit my job and went to grad school to get a master's and PhD. And I thought, AI is the future, and I'm going to go do AI. And I chose my graduate school because they were working on neural networks, these cool things that had this amazing promise. And I got there and I studied them, and I finally decided this isn't going anywhere. And actually, in my defense, for 30 years I was right. But back then, it was the shiny new thing, and if you told anybody you were skeptical, it was like going to a church picnic and telling people you were an atheist. You got really dirty looks. And I get a lot of that sense now. And there was a huge amount of hype that didn't pan out. And I get a lot of that sense now as well. I feel like history is repeating itself with a big difference. AI clearly works now. It clearly didn't work then. But I'm not convinced it works as well as people think it does. And I think for things like taking a photograph of a bunch of vegetables and saying, if I made a salad out of this, how many calories would it be? I think that's a great use of it, and because you don't really care if it's wrong, as long as it's, as
You
long,
might care, though.
Well, yeah, but as long as it's right most of the time or in the ballpark, it's okay. In circuits, it's a lot different because we really, really care if it gets it wrong, right? And so I really do worry that it's not the ideal application. Also, what a great application for AI is where you have a very ill-posed problem. Like you can't, if you want to make an app that recognizes a dog, for instance, you don't tell it how to recognize a dog. You don't even know how you recognize a dog. It just does it. It learns it. But in circuits, we have very specific guidelines and methodologies, and so it's just not clear to me that it's the ideal application. So I'm a little skeptical. I'm open to being convinced otherwise, and maybe these guys will convince me. But
You don't want to tell the computer to, do all my corner simulations for me.
oh, I'd love to
Summarize the data, all these types of things.
I'd love to do that. I'm
Yeah.
just not convinced that it will do it right. So like I said, I'm skeptical, but I'm open to being convinced otherwise. But so far, I haven't seen evidence of it.
Thomas, maybe your comments on.
I'm not sure I'm qualified either. Primarily because my background is more in digital design. But we've been looking into AI and ML for digital and analog for some time. I'm wondering if the panel, if we improve or reduce our skepticism, I'm not sure. But I would argue I'm skeptical also. And I can tell you a little bit about our journey. So initially, before the current AI hype, we were looking more into machine learning algorithms. For example, within our EDA tools, build predictors for certain heuristics. They mostly didn't work. There's some things that worked, like, for example, in simulation, avoiding lots of Monte Carlo expensive simulations by predicting that in some cases you don't have to do it. Things like that may work. In many other cases, it didn't actually work that well, primarily because we didn't have enough data. That's one thing. The second thing is I'm actually, so when we use the word AI, I always say, so there's many technical definitions of what AI is. I always say, I want to automate the task that a human is doing today. Tasks that, for example, an EDA tool does, optimization, things like that, timing analysis and so on. These are not human tasks, actually. I mean, maybe at some point they were, at a very small scale, that's true. But replacement of core algorithms that are used for optimization with other techniques, like, for example, a few years ago, there was this Nature paper from Google. I don't know if any of you are familiar with that, because it's more in the digital domain. There was a paper essentially saying, well, we can do macro placement with reinforcement learning much better. In the end, it turned out that wasn't true. Anyway, so we have not seen that any such techniques have actually replaced core algorithms. And now I'm going back to what a human does. So does a human place millions of or 1,000 cells or millions of macros? No, he doesn't. Computer can do computationally much better jobs. However, there's tasks where I think AI can help. I think they're more assistant tasks. They're things like, for example, workflow optimization. Somebody runs lots of experiments and tries to figure out some trade-offs. Yeah, I can use an AI optimizer for that. Even in AI circuit optimization, it's a very tricky problem where I think traditional optimizers don't work so well because the function that I'm trying to optimize, like things like conjugate gradient descent methods, may not work. Maybe discontinuities and other things. So there are other techniques, more ML techniques that could be better.
I think that's been kind
Right.
of like to simplify the number of simulations to get to an optimal.
Correct. So I think that has proven to work. And then since you mentioned the word copilot and generative AI, I think there's definitely potential for things like suggestions, like helping the human, like taking a natural language document and coming up with a spec, maybe suggesting some things, but I think we're lacking accuracy. At this moment in time, no LLM has complete accuracy. Like you cannot even like GitHub Copilot, you cannot write code with it and then say here compile and it works. And that's a big problem. So you cannot optimize, you cannot guarantee accuracy, and I think this will be a bottleneck for I don't know for quite many years.
Thanks. Yeah, no, I think it's exciting because it's just starting, right? There's been more and more discussion of, using machine learning to design circuits. And I think the number of publications are also going up. So I think it's an emerging field. And there's also the layout aspect of it that's going to be, and so my thought is that anything that we find tedious, repetitive, or it could also lead to a tape out of it, kind of a high consequence mistake. We look through, DRC errors and ERC errors, those types of things that'll really make things more robust. And as you know, these days, the cost of a tape out, especially in like the advanced nodes, is very expensive and a lot of IP goes into it. So anything that we could use to sort of, reduce that iteration, it's a huge, huge impact. So Naveen, we're kind of open, just, what do you guys think about it? And then we can go more into the details and maybe leave some time for questions.
I'm going to take a glass half full approach. I'm not too much of a skeptic on this. I think this can be done. And the onus is on the engineers to take on this task to make this happen, in my opinion. The more lazy we are, the more motivated we would be to make this happen. I've been an RF circuit designer for a long time, like Kamal was. And now I just manage Excel sheets and business. So I see both sides of the world. And I think the motivation has to be that what used to take 10 hours or 10 engineers should be now only one engineer or 10% of the engineering time. I was thinking of an example, very simple example for those of you who are in RF design here. We, for example, take a very simple design like an RF switch or a low noise amplifier. There are only so many architectures, so many technologies you would choose to fulfill a specification to meet the performance. All the way from what an engineering aspect takes from initial conceptualization all the way to production. If you think about it, every step AI can help a lot to reduce the amount of work and also improve the performance. From product definition, when a customer comes up with a specification, if the model is trained very well on the RF switch and it understands the RONC of parameters of the technology, underlying technology, and the various parameters that you're trading off, be it insertion loss, isolation, bandwidth, or whatever else, there could be a back and forth that could be done with the customer without a product definer involved as much, or maybe involved to 10% of the time that previously they were involved.
So you're talking about translation of specs?
Translation, exactly, and get to a data sheet with very little effort. And then once the customer says, yes, this is the data sheet.
I guess then you can pick from your database and it automatically designs it as well. Is that
exactly? There is enough data that is trained. You every time a circuit designer runs a simulation, the netlist as well as the outputs are recorded and trained by the model, and then the model gets better and better.
I think that's one of the challenges. Is we have a lot of data, and especially analog RF designers, they're very much like herding cats. So they don't have a standardized format of naming things or test benches. So doing those types of things will allow the machine to kind of understand. So we have to and I think that's one of the things of like the design engineer would. I think organic engineering isn't going to go away. It's just going to be augmented with inorganic. Sorry, I'm using the word organic, but the design engineer will have to learn maybe new math, because now it's more about optimization. How do you minimize these cost functions? And what you're leaving out of that optimization may be important. So I think it's in a way, a different way to sort of speak to your simulator or your cadence environment or your Synopsys environment or whatever environment.
The question I have is, would you ever come up with something new? I mean, what you're describing, I know precisely what you mean, but you sort of repeating what you've done before in some variation of it, right? So that's a big question. I mean, none of our engineering tasks is, I mean, there are people that probably just churn out similar designs all the time, but a lot of it is also creativity in building new things.
Yeah,
That's
that's
true.
what, if a lot of this, I think, take a, I think you use this word, you need to execute to innovate and innovate to execute one time. But yeah, if all of this execution can be simplified and 1/10 or 1/20th or 10% of the engineering time can be used to churn out the regular designs, then you have more and more time left for R&D engineers to look at more circuit architectures or whatever else.
There's a
Yeah, no, it'd be good to also hear from Mark and Michael on the other end. So sorry, Mark, I know you had.
No, I mean this is a big topic, and I probably take some comfort along with Ian that I think with the level of hype that's around AI, I'm definitely in the skeptical bucket. But having said that, if you narrow the problems down sufficiently, then there are solutions out there, and we've actually had a solution on the market for a number of years around using an ANN model for modeling GAN devices. So it's called Dynafet. I guess we've been using it internally for probably more than a decade, 12 years, 14 years, something like that. And it's been available for people to use. In fact, I was talking to some folks about it recently. And it gives really good results because we don't have a good physical model for a GAN device. We don't really know how it operates, but we can, take a set of measurements across the state space and interpolate appropriately and get some really good results. So I think there are some good examples of where AI can add value, but it's just another tool in the armory. It shouldn't, I think, be used in this kind of, it's going to solve all the world's problems approach. So, we've heard a little bit about anomaly detection today. That's fine. I think definitely that's in the bucket here. We've got solutions where we're using AI to get a faster pattern generation to find a particular case. So in this world, it would be, okay, I want to go find the corners of your design. Mm-hmm. How do you do that? I think you can absolutely do that with AI. So I think there are some areas where you can save huge amounts of time. And what we're really talking about here is productivity, right? However you choose to then take it, you can convert that into money on the bottom line or redirect some of your resources to the more complex problems. And I definitely share the view that if everybody designs everything with AI, you're just going to end up with some convergence to some, where's the differentiation then, right? That's a problem. One of the things I haven't heard about today at all, and we're really talking about what I term physical AI here. In other words, we're not generating pictures of tomatoes or images of whatever from prompts. We are talking about things that turn into something really physical. And so the stakes of getting it wrong are very large. Yeah. And so within this whole cyber physical closed loop system, whether that's robotics and, the robot smashes whatever it is that it's trying to build or move.
It violates the first law of robotics.
Completely. So I think we have to be very careful about how we apply this. And just to pick one kind of other area, it's around this whole data challenge. We're spending a lot of time doing the work, thinking about it. We're within the NIST panel as well around, how do you test AI? I mean, that's a huge issue, right? Because AI is a combination of algorithm and data, and they change. The answers do not stay the same.
Yeah.
So you have to have some way of dealing with that. I think we're going to have to come up with some much better ways of assessing the data. We had some discussions earlier of maybe a digital twin was a way to do that, to help you fill out the data sets. Everybody used to say, well, Tesla's in a great place, right? Because they've got all the data they're sucking back from their cars all the time. But I don't think it's helping them much with their self-driving. Partly because if you think about all the data, yes, they've got terabytes of it, I'm sure, maybe petabytes of it, but it's all regular driving. How often do you bump in or see something unusual? How do you find more data of the strange kind of anomaly that you want to capture and then respond to? Yeah. So I think data, and fundamentally, I think we're missing a lot of the ontology to be able to combine that data in really valid ways. And it's interesting you use the term, RF engineers are kind of, running around in the wild, but nobody's got a consistent
part of the
way of
nature.
keeping all of that data together and using it. So
Yeah.
anyway, leave some time
Yeah,
for
Michael,
Michael to
it'd be
comment.
great to hear your thoughts on that.
This is interesting. I may be the optimistic one on the panel, which is surprising. But I will say, Veen has a very good point. After you design your first switch or your second switch, it's really pretty boring after that. It's done it before. It's not that interesting. But you may need one at a different node. And certainly if you can provide a machine learning capability that takes that and translates it to a different node, looks at the test benches you've had before and optimizes for the same parameters, and uses maybe the previous layout as a guide and lays it out for you, and just migrates that entire switch to the next node, that's probably pretty valuable. It's probably something you didn't want to do anyway. And that's certainly the work that we've been pioneering in the Virtuoso Studio platform this year. And we have been doing this with customers. So we have cases where we've done migrated designs and they met spec, they got built, and they got deployed. Cadence has been working in this area for a pretty long time now, and going back to several DARPA programs and things. But one of our first products was a product called Cerebrus, more in the realm of processors and SoCs and ASIC design, where you have some very clear goals, so your PPA, power, performance, and area. That's exactly what you're trying to do. So Cerebrus looks at place and route of a very large design that's probably some RTL synthesis design you've given it. And it goes and it looks for the optimal size to improve the power and the performance. And it's I know it's helping customers now. It's producing designs that they are coming back. I mean, it's not like saying, okay, I went from this huge design to something that's tiny, but it's 10 or 15% better. And when you start reducing your size on your wafer that much, you start to see, dramatic differences in costs and certainly additional profitability that you wouldn't have seen before. So I think there are some areas where
I think the second source example, or porting the design to another foundry, is really great because you have the sort of the reference design, and then that's something that you already have the training data essentially. Just also, one thing I want to point out is we're using at Qualcomm for the characterization and testing of using artificial machine learning, because that's an important part. And on our RF chips, we have thousands of registers that the many different circuits that are all programmable, and then coming up with the proper settings that will yield and high volume production over the various environment is also good. We've really been able to kind of reduce that time, and I think there's still a lot to do. And then once you get into high volume production, you're generating tons of data. I think we have like 800 million chips a year just in the RF side. So you can imagine how much data that we have and how much time we're using to spend testing. So I think that's another aspect that we can use some of these tools to reduce kind of the overall test time, not of like one particular device, but the average test time. So there's a lot of other these types of things. And I think we're about 2 minutes left. So any more comments from you? I know this is a very broad and deep topic, and half an hour is not really going to cover it, and we're running a little late. So I understand that, but I do want to say that eventually I think we'll also be adding maybe small neural networks, as adaptive filters on chip to maybe deal with the environment, aging, and things like that. So automatic generation of parameters as well. So that, there's a lot of things we could do. And I would say I'm half more optimistic about this, just because it's another tool, and it's not, and whatever tools we can use to kind of make our lives easier is always a good thing. So, yeah, any questions from the audience or any comments? That would be.
I guess I have one for you.
Sure.
You're obviously in industry at Qualcomm. Are we going to have to develop these tools simply because you can't find people to do these jobs in the future? Is that where we're going? That seems to be where we're going. I would love to hear your comments.
I think there's, it's luckily so far there's people still, I think the enrollment into RF engineering is lower than usual. And I think in particular, sort of students from the U.S. themselves. So I think
Ironically, because they're going into AI.
right. So it's sort of like it's kind of chasing our tails in a way. No, but I think that'll has a factor, but I don't think it's because I think the creative aspects is still going to be needed by because it's sort of I would imagine the tool is only bounded by the training data that it has to produce something. But you could see that if I was thinking what if you could train a model that has all the IEEE publications in every field, all the textbooks, and could it come back with something that's more new? I don't know, but it would require a lot of computing, but you could imagine that would be very powerful.
You mean come up with new algorithms or something, or new?
No, it's just if you imagine it had all of the data, everything. Mm-hmm. You've read every book about every possible subject, and if you asked it prompt, it would give you an answer.
There is, I've not seen it in practice, but technically generative AI or LLMs can apply a technique from one domain to another. So that may work. For example, like in EDA, things like placement problems, they originated in graph theory. And some of the early algorithms came from there. So there may be transfer of some, but coming up with something brand new, I don't know. I have a hard time envisioning it.
There's also a danger, which is that, when we got calculators, we all forgot how to add and subtract, right? And then when we got spell checkers, we all forgot how to spell, right? And so if we actually have machines that think for us, that's really dangerous, right? So,
you know what? I disagree on the spell checker. Because,
it's true for me.
Well, because so I'm pretty good at spelling, I'll be honest, but if I do something wrong, I can see it's underlined and it helps me. That was wrong. Helps me learn. You know what I'm saying?
You're not lazy
It's
enough.
not like I'm writing an email and then I say, okay, autocorrect everything and then send it off. As you type, it will tell you this is wrong.
Yeah, I get that, but
Right?
but I also take the view that it since it will tell me every time, I don't have to pay too much attention.
Exactly.
Okay.
That's me. Yeah, I know I'm gonna get it wrong anyway, so I just get to the ballpark and let it correct for me, right?
Yeah, I think it's something we'll have to experiment with, and the good news is that there's commercial tools now starting to become available that will, allow us to do more things with, maybe with less or do things more deeply. And, but I think it'll require a lot of computing power. So it'll be interesting how much extra compute we may be wasting because you're going to be running a lot more simulations. And even some of the simulations large chip simulations can take a lot of time, huge amount of time. Yeah. So it's not gonna, those aspects, like when you have a simulation that runs 3 days, it's going to be very slow. So, so computing power will become also a key aspect. I think
the computing power is there, the models are there. I think what is needed is more motivation. I think somebody needs to step up. I mean, we're on UCSD campus today and make it happen. I think has to take the bull by the horn and work with some AI engineers and make it happen. And take one step at a time, baby steps, and show it working for one particular application and then let it proliferate.
yes. A question for Shara.
Yeah, a quick question for you. I think something that I've noticed, especially in the education part, so we are approaching this because we already know how to do this. We are at the transition, right? So we know how things are and we're looking at how things will be. But the new generation of students won't have that benefit. And I think being on a transition is a very different experience than being once it's been established. I have interviewed students to come work in ASICs where I asked them, how did you size your transistor? And they said, I Googled it, right? I mean, is that how it's supposed to be? Because that's a very different kind of answer, right? And I think that we have to be somehow prepared for that. We can't just put out these tools and not adjust something else in the parameter, which is the training of these students. Otherwise,
if the tools work, then I don't have to do it anymore. You can think this analogy that you bring, you can think about this the whole life. Like at some point in Switzerland, they were watchmakers and they were making like watches and they had all these skills to do them. And at some point it became obsolete because it wasn't required anymore. So if the tools work, then that job just isn't needed anymore.
Yeah, but the watch might have become obsolete, but the mechanical skills to understand how those
I think we'll still have to teach the fundamentals. I think that's as a UCSD graduate, I think that's what I'm proud of. So
That's true.
but let's maybe continue this discussion. I think we're out of time. So thank you.